Guys, so please type in the chat box. Is the audio and video fine? Yeah, good evening guys, but please type in the chat box. Is the audio and video fine? Actually, fine, right? Okay, good. Then we shall continue undoubtedly. So yeah, welcome you all. Basically, this is the second lecture of this course, actually, engineering mathematics. So in the last lecture, we have given the details of the outview of the course, how the course is going to progress, what all modules we are going to cover in this particular course. Okay, so we have roughly divided the course into 10 modules. Okay, and in today's class, we will look at the second lecture of linear algebra. Okay, and today's lecture basically will be inclined towards learning this matrix algebra, of course. And before going to the course, if some of you are new, so this is a maths batch basically which was launched yesterday, and we are going to cover the complete syllabus of engineering mathematics, which is relevant to the syllabus of mechanical, civil, EC, TEEE, computer science, chemical, XE, and also data science. Okay, so these branches will get benefited definitely out of this course. Okay, so this is the Get Wallah English channel, telegram channel basically, which we have recently launched, and any update regarding any lecture on this channel will be given on this group. Okay, so I request all of you to please follow this group, so that if you have any quick update, that will be posted on this group, of course. Okay, and this is my group, which is maintained by me and my students, of course. So this is the group for which if you want to get connected with me personally, you can just scan this group, and it will directly, by scanning this QR code, it will directly redirect you to the group actually. So you can just click on join, of course. Okay, and we are going to start today's second lecture for this linear algebra. And if you have a quick review of the last lecture, what we have discussed in the last lecture, so we have introduced the concept of a matrix. Then we have seen the initial notation of writing the terms, where I and j are the row and column numbers respectively, of course. And then we have started looking at types of matrices. So we have seen square, diagonal matrices, upper triangular, lower triangular. So like if you just see, in last class we have talked about the triangular matrices exclusively, triangular matrices, and then after we have talked about basically this diagonal matrix, and we have talked a special case in that, which is scalar matrix, of course. And we have talked a lot of other stuff as well. Okay, so we have talked about identity matrix, okay, null matrix, and then after we at the ending of the lecture we are talking about transpose and its properties, of course. So we have talked about we have talked about transpose of a matrix, and from transpose we have talked about two types of matrices, which is symmetric and skew symmetric. Okay, so symmetric and skew symmetric matrices. So in a broader sense, this symmetric matrix is, of course, Aij is equal to Aji for all the elements, and here there comes a minus sign which flips the element, of course. Okay, so minus Aji. These are the things that we have covered broadly in the first lecture. And are you all clear till this points? Any doubt from the last class? Please type in the chat box. If you have any doubt in the last lecture, I'll just clarify it, or else we'll start things for today. So if there is no doubt, we'll continue with the types of matrices actually, and then maybe in the second half of the lecture we'll look at matrix algebra. Especially we'll put some special touch on the multiplication of matrices, which is very important actually. Okay, so please type in the chat box. Is this clear to all of you? Yeah, everyone quickly type in the chat box. Is everything clear so far? So shall we proceed with this lecture? Good evening all of you. Okay, so shall we all proceed? So just skew symmetric. Yeah, basically in the skew symmetric case, what I have told you is, in the skew symmetric, like in a broad sense, this matrix, any matrix A of the form, the negative of the transpose is equal to itself. Okay, so in such case we have this A equal to A transpose, and we have seen this Aij element, means element in the ith or jth column will be exactly negative of the element in the jth or ith column. And we have seen two properties of the symmetric matrix. First property, principal diagonal elements are zeros And second thing we have seen is basically sum of all the elements. Sum of all the elements is also 0. Is also 0. So these are the points I have shown you basically by doing simple analysis in last lecture. So I just want to give you a few points again, which before going for other types of matrices and multiplication of matrices, we want to talk here about basically we want to talk about some important points, actually some nice points. Look, first point that I would like to tell you is every square matrix can be written as or can be decomposed into sum of a symmetric and a skew-symmetric matrix. This point is really important. Okay, a skew-symmetric matrix actually here. Okay, so this is skew-symmetric matrix. This point is really important, of course. Okay, why it's really important is because many times, of course, maybe the points what I'm talking is slightly out of the scope of this course, but sometimes when you find equations which are difficult to solve, whenever you are splitting the matrix into a symmetric part and a skew-symmetric part, many times it happens that when you multiply any vector to a skew-symmetric matrix, that outcome can be 0. Okay, because I'll tell you why. When we teach the concept of eigenvalues, you'll come to understand. Let's say if the vectors are in such a way that 0 is 1, if the matrix is such a way, it's an odd order matrix. Let's say if you are dealing with 3 by 3, definitely every odd order skew symmetric matrix will have 0 as one of the eigenvalues. Okay, we'll see why this is happening. So ultimately, whenever you multiply this vector with A, there is quite possibilities if the vectors are along the eigenvector directions, then ultimately you'll get 0, and that particular term which is causing the trouble will get eliminated. Okay, so anyway, that's a bit of advanced things, but we'll see the things which are related to this course and gate syllabus domain within. So let's see how we can do that. So let's say if I take a matrix A, let A is equal to P plus Q. Okay, so this is two matrices. Let's say this is symmetric and this is skew symmetric. Okay, so first of all, will you all agree if I write A as, we can write A is equal to half times A plus A transpose plus half times A minus A transpose. Can I write it this way? Because A transpose by 2 gets cancelled. Yes or no? Can I write this? Please type in the chat box. Every one of you. Creator, Surya, CR, Samiksha, Kids Gaming, okay, Hema, Tanisha, all of you. Can I do this? Yeah, because if you just add these two matrices, A transpose by 2 and minus A transpose by 2, they gets cancelled, and finally you'll get the outcome as A again, right? Now, if you check, if I say let P is equal to half times A plus A transpose, so you consider this. Let us inspect what does a matrix plus its transpose always gives us. Okay, a matrix plus the transpose of that particular matrix will give us something like this. So this implies P transpose is equal to half times of A plus A transpose whole transpose. Okay, so in yesterday's class I have told you, if you multiply any matrix with a scalar and if you take transpose, this scalar do not get affected, so this scalar stays as half here itself. Now if you apply the transpose to this inner matrix, you have A plus A transpose whole transpose. Okay, so this is what you get. So half into, now you can see whenever there is sum of two matrices and there is a whole transpose, you can break this whole transpose into sum of individual transposes. Okay, so breaking this into two matrices, first matrix power transpose A transpose plus the second matrix is A transpose whole transpose. And yesterday's class I have told you, if you transpose any matrix even number of times, you will get the same matrix again. Okay, so first when you transpose, rows and columns gets exchanged, and second time when you transpose, again the current rows and columns get exchanged and they restore the original position of the elements, so this becomes A. And if you observe carefully, this is same as this matrix which is P. So initially we started with P transpose, but finally we got P, so that means this matrix P is a symmetric matrix, and since I have taken this as P, of course, so this part of the matrix which I have written, this is always a symmetric part. Okay, so in fact forget about this constant, because constant do not change the symmetricness of the matrix, but this A plus A transpose will always be a symmetric matrix. Okay, similarly if you have Q, for example, let's say let Q is equal to half times A minus A transpose, for example. Okay, so if you consider Q transpose, again the same story, half into A minus A transpose whole transpose, so half do not get affected, A transpose minus A. So if you take a minus sign common, minus 1/2 times of A minus A transpose. Okay, because A transpose minus A is equal to, if you take minus common, then it becomes A minus A transpose, and this minus sign if you keep individually, then this 1/2 times A minus A transpose is nothing but your Q. So you can identify your Q transpose is actually equal to minus Q, of course. Okay, so Q transpose is equal to minus Q. So that tells you this matrix is 100% skew symmetric and this is asymmetric. So that's why any matrix can be decomposed into two parts, which is a symmetric part, and out of them the other part is a skew symmetric part actually. Clear to all of you? Yes or no? So please type in the chat box. Is this clear to all of you? So every matrix can be split up into a sum of symmetric and skew symmetric parts, where sum is the matrix plus transpose of itself, and skew is basically a matrix minus transpose of the same matrix. Okay, so that's what. So where P is equal to half times A plus A transpose and Q is half times A minus A transpose. Okay, P is symmetric, P is symmetric, and Q is skew symmetric. Okay, so that's what you have. Next, let me ask you one thing. The number of symmetric matrices of size n by n that can be formed using the elements 1, 2, 3, 4, 5, 6, 7, 8, 9 is dash. And since n can be greater than 9, because I have generalized the matrix, so you can allow the repetition of elements, no issue. Okay, if you want to repeat the elements, you can repeat, no issue. So can you tell me how many elements you can form? So let's say, for example, if I give n is equal to 3, okay, so say for example, say n equal to 3 in this case, okay, because I just want you to type some answer in the chat box. So if n is equal to 3, then how many matrices of size 3 by 3 can you form such that the matrix is symmetric matrix and the matrix involves these elements? Okay, so I'm starting a poll in the type. Maybe I'm giving some 90 seconds of time. You can start. Come on. So please type in the chat box. Arvindan, Gautami, Sagnika, Vasishta, Kotla, Manoj Kumar, Tanisha, every one of you, Hema, Satvik, Surya Prasad, all of you. Yeah. Come on. If you want to form a 3 by 3 matrix using those elements, of course, if you want, you can repeat the elements, no issue. So how many matrices you can form? Okay. How many matrices you can generate using those elements such that matrices of size 3 by 3, and you can option A. Options been A. Okay. Five. Okay, maybe. Come on, the time is running up. Quick, think a while, you can understand. Fast. Three matrices. You can form only 3 matrices, Thomas. Vasishta found 5. Arya has found 5 actually. 16. Tanisha got 16. Fine. Okay, the poll got ended. Okay, meanwhile. So let's see. Okay, 9. Fine. Samiksha is telling 9. Let's see. Okay, so let's figure out how many matrices you can form. So I'll explain you one thing. Say for example, you start with n equal to 3. A will be of the form A11, A12, A13, A21, A22, A23, A31, A32 and A33, of course. Okay, so let's say these are the 9 elements in this matrix. Now 6 into something. Okay, let's figure out how many we can do. So see here carefully, I told you this matrix has to be a symmetric matrix, which means if I specify this element, then I need not specify this element, because if I fix some value here, the same value I should fix here. I do not have the choice of fixing some independent variable. Okay, so if I fix A12, if I lock A12, then I cannot do anything with this element. Similarly, if I do this, I don't have choice for this. If I fix this, I cannot have choice for this. And I have the choice, whatever I want I can fix in the places of A11, A12, A22 and also A33. Correct? Means along with diagonal elements, I only have the choice of fixing either lower diagonal elements or upper triangular elements. Correct? Will you all agree with me? Yes or no? Please type in the chat box. Means if I want to form a symmetric matrix, then I have the choice of making principal diagonal elements, and along with that I can choose either upper triangular elements or lower triangular elements. That's it. I cannot choose both independently. Right? Now let's see how many choices I have. First of all, how many spaces I have. I can choose this element. So 1, 2, 3. So in the first row I can fill elements at my wish in all 3 places. Second row I have only 2 choices available. Third row I have only 1 choice available. Okay, so total I have 6 places where I can fill my choices in order to form this matrix. Okay, now since repetition is allowed, can anyone tell me in each of these places how many choices do I have? Means let's say if I want to fill A11 using any one of those digits, how many choices I have to fill this particular digit? To fill this particular element, how many choices do I have? 9, right? So similarly, to fill this place again I have 9 choices. To fill this place again I have 9 choices. So similarly, I can fill at any of these 6 places using 9 choices actually. So total number of symmetric matrices I can form that can be formed is equal to, see, in each place I have 9 choices, so likewise I have total 6 choices to fill. Okay, so these 3, 2 and 1, so total it's 9 power 6. Okay, so 9 power 6 is equal to, so what is the value of 9 power 6? Let us take a calculator to punch some keys. 9 power 6, so 531,441, 531,441 means you can form 5,31,441 matrices such that they are symmetric using these elements. Okay, 531,441 actually. So you can form more than 5,30,000 plus matrices such that using these 9 elements, and such that it's a 3 by 3. Okay, if it is not 3 by 3, if I increase the size, let's say if I ask you 4 by 4 matrix, okay, then ultimately, so let me generalize some expression. Okay, so if you want to form in general a n by n matrix, then look, in general if I take A is equal to A11, A12, A13 and so on, A1n, A21, A22, A23 and so on, A2n, A3 and so on. Okay, so just let me write the things. So let's say it's a n by n matrix, so an2, an3, ann. Okay, now first of all, in the first row I'll have the choice of selecting all n elements. Now by the time I have selected this, I lose the basically the command on this element because it is locked by default. So in the second row I'll have only n minus 1 elements to pick. In the third row I'll have only n minus 2 choices. Okay, and in the last row, by the time you come, you'll have only n minus of n minus 1, which is only 1 element, of course. Okay, because you can see only this diagonal element will be left with me. All other elements would have been locked because I have already chosen my elements here. Okay, so you can see in the second row you have n minus 1, in the third row you have n minus 2, so in the nth row you have n minus of n minus 1, which is 1, of course, and you have only this principal diagonal element to fix actually here. Okay, now total number of places available, available for choosing is equal to sum of all these places, correct? So this gives you n plus n minus 1 plus n minus 2 plus and so on plus n minus of n minus 1. So this expression will actually give you total. There are n terms. In each term, first term is n. Okay, so you have n in this term, n in this term, n in the third term. Similarly, in the nth term also you'll have n. So total you'll have n times of n actually. Okay, then after if you subtract minus, okay, sorry, n minus of n minus 1, how? Look, because in the second row I have choice of making n minus 1 elements. Okay, since this is second row, this number is 1. In the third row I'll have 2 here. So if this is the nth row, I'll have n minus 1 here. Understood? And ultimately if you simplify, this value is 1, and you know by default you have the choice of choosing only the principal diagonal element. You cannot choose any other element in that row. Okay, Thomas, is this clear? Fine. Now if you simplify this, after taking this n's, then you have this constants 1, 2, 3 and so on till n minus 1, of course. Okay, so that tells you 1 plus 2 plus 3 and so on plus only till n minus 1, of course. Okay, because the last term ends with n minus 1, it's not n. So if you simplify this, this value gives you something like n square minus, what is this value? Sum of first n minus 1 natural numbers. So n minus 1 into n minus 1 plus 1, which is this, into 2. So this gives you n square. So if you take n common, then you have 2 minus of n plus 1. So this gives you basically 2n minus n. So this gives you n square plus n by 2, correct? Yeah, ultimately, right? Because you can see if you take n common, then this is 2n minus n, so that gives you n minus of minus 1, it's plus 1, so n into n plus 1 by 2. So this is n square plus n by 2, of course. This is what you get. Clear? So these are the total number of places you can make your choices. And now in each case, if you have k choices, let's say for example if I given you, you can use k numbers 1, 2, 3 and so on. K numbers can be filled at any place, then number of symmetric matrices that you can form, is equal to k power n square plus n by 2. That's what. Okay, so because for filling each choice you have k, for filling each place you have k choices, you can pick any one of that k. So k to the power n square plus n divided by 2 gives you the actual answer. Got it? And if you apply the same logic here, I have 9 choices in each place. So 9 power, I want to form a 3 by 3 matrix. So 3 square plus 3 by 2. So 9 power 3 square 9 plus 3 12, 12 by 2 6, 9 power 6. That's it. That's what even we got by counting physically. Okay, is this clear to all of you? Yes or no? Please type in the chat box. Is this clear to each and every one of you? Did you all understand how this 9 power 6 and basically that the generalization k power n square plus n by 2, all these are in sync with each other? Okay, yeah. Now let's get into bit of linear matrix algebra, because I want to discuss a few other types of matrices like involutory, idempotent, all these things, but before nilpotent. Okay, so but before I go there, I just want to talk a few things about the matrix multiplication actually. Okay, because I know some of you might have forgotten matrix multiplication because you might have done in schooling or +1 level, but let's have a quick review of how to do the matrix multiplication and what are different points that we can get if you do matrix multiplication. So let's see matrix multiplication. How many of you did not remember? Oh, sorry. How many of you don't remember how to do matrix multiplication? Tell honestly. It's okay. If you forgot, it's fine. How many of you do not remember matrix multiplication? How to do multiplication of 2 matrices? Or how many of you feel confused when you're doing multiplying 2 matrices? Because initially when I was in school days, I used to get confused many times. No one. Everyone is sure with matrix multiplication. Good. Then my job is easy. Fine. See, when I ask something, please say, okay? Even if one person asks for it, I'll definitely say it. If you don't ask, I'll be the happiest also, okay? So let's see matrix multiplication. So ultimately, a matrix A m by n and B p by q are feasible for multiplication, are feasible for multiplication, are feasible for multiplication if you know ultimately n should be equal to p, of course, okay? So you can multiply two matrices only if this is there. So last Wallah, please explain first row into first column, okay? Likewise, so last Wallah, please explain this one, this one. So basically what I'm telling you is, when you are forming a symmetric matrix, you have the choice of only these number of elements, okay? Like for example, in this matrix total, you know, since it's of size n by n, total you will have total n square elements, but out of that n square elements, you will have only n square plus n by 2 choices for you to fill. That's what we have shown here actually, okay? Now let's see, in this case, I'll just show you, if you have a 2 by 3 and let's say you have a 3 by 2 matrix, then ultimately you know the result is going to be a 2 by 2 matrix, okay? Because if this is 2 by 3 and this is of size 3 by 2, first of all, for the matrix multiplication to happen, these two numbers should be same. That's what I have told you. N should be equal to p, and whatever is this m, and if this is your q, then this is of the size m by q, of course, okay? Let's work it out with some examples. Let's say 1 2 1 3 minus 1 4, let's say, okay? This is 2 by 3, and if you take 3 by 2, so let's say 2 minus 1 1 minus 2 1 2, okay? So let's take some elements. If you want to multiply these two matrices, how you are going to multiply is, in the product you want the first, clearly it's a 2 by 2 matrix, you know, it's a 2 by 2 matrix, okay? Now if this is a 2 by 2 matrix, then you know, if you want the first or first column element in this product matrix, okay, if you want the first or first column matrix, then you should take the first row vector here and you take the first column vector in this matrix. Normally this A B product, if you have this A is called prefactor. Why I'm telling this, it's important, I'll just show you in few in some time, okay? So prefactor, and this is post factor, actually post factor, okay? Now let's see, if you want the first or first column element, you take the first vector, I mean first row vector in the first matrix and first column vector in the first matrix, I mean in the second matrix, and you do the dot product of these two vectors, okay? So let's say this is the vector, first row vector, and this is the first column vector. Then you do the dot product of these two vectors, 1 into 2 plus 2 into 1 plus 1 into 1. This is how you actually get the first or first column element. 2 plus 2 4 plus 1 5. Similarly, if you want first or second column element, do the dot product of this first row vector with the second column vector, okay? So 1 into minus 1 minus 1, 2 into minus 2 minus 4, so minus 1 minus 4 minus 5 plus 2, this is minus 3. Then 3 into 2 6. Similarly, if you want second or first column, second row vector with first column vector, 6 minus 1 5 plus 4 9. Then minus 3 plus 2 minus 3 plus 2 minus 1 plus 8 7, okay? So this is how you're going to get this matrix, resultant matrix, of course. And many of you might have studied, if you want to write a program for this, how do you write this? If you want to say, for example, A B is equal to C, how you write? Cij is equal to Aik Bkj, you remember? And this k is called, since k is coming twice, it gets repeated, okay? So like for example, you can say this matrix is equal to summation, or this element, any element in this matrix is equal to A k equal to 1 to n. Let's say if you are getting a total of n columns, means basically this is n, okay? This is n what I'm telling. So k equal to 1 to n, Aik Bkj. This is how you'll get the element in the product matrix, actually, okay? I think many of you might have written a for loop in order to calculate matrix multiplication many times. So this is what you might have done, actually. Yes? Yes or no? First of all, you define Cij is equal to 0. Then you write for k equal to 1 less than. So for k equal to 1, k less than or equal to n, k plus plus, you might have written Cij is equal to Cij plus Aik Bkj. You might have done this thing. Yes or no? Is this what something you might have done? Yes? Did you all do this at some point in your life? Many of you might have done C language in your BTech first year. At that point you might have done this, or maybe if you are already passed out or somewhere, then I'm sure many times you might have come across that particular loop of doing two matrix multiplications. Correct? No? No or yes? Did not? You have never done this? If you have never done, forget, don't, no issues. Okay, I'm hiding. Okay, maybe I'm fat enough to hide this. Good. Yeah. Okay, if you understand this, it's fine. Clear? So let's see. But anyway, this is just a logic. Normally if you want to crack some codes, then that's how you basically multiply couple of matrices. Like I can just tell you, if you want, for example, C11, I'll explain you this. Forget about programming part. Okay, anyway, we'll deal this later, maybe in some other course. Now let's see. What I'm doing is, if you want to calculate, for example, C12, okay, so let's say you want to calculate C12 element. So I'm fixing I equal to 1, j equal to 2. Okay, so if I fix I equal to 1 and j equal to 2, this is C12. Now how do you get this? You get this by multiplying first row with the second column, correct? So you can see first row is A11, A12, A13, second column B21, B22, B23. Okay, this is what you might have done. Okay, now let's see, if you multiply this first row with this second column, you'll get the first row second column element. Okay, so let's see how you'll get C12 is equal to A11 B21 plus A12 B22 plus A13 B23. This is what you get, correct? Now let's see. Fine, yeah, everything is I think it is JK. Okay, sorry, this is JK. Yeah, this is JK, AIK B JK. If you write, then you can see A11 B21 plus, because I have fixed this 1 and 2 here, so you can see since I have fixed 1 and 2 here, then ultimately this should be 1 and this should be 2. Then you can see when you are on the loop, A11 B21 plus A12 B22 plus A13 B23. This is what you will get actually. Okay, that's what. But I think just a minute guys, I think because I'm pretty much sure it is JK actually, I mean KJ actually. Yeah, something happened. Yeah, ultimately no, this is like 1 2 2 2 3 2, correct? Because it's in the third or second column, so it should be 3 2. Yeah. Okay, is this clear? Because ultimately if I want to write the second column, this is how I should write it. So I should fix the second index. Okay, then ultimately that formula holds good. Yeah, 2. Then it should be B12 A11 B12 plus A12 B22 plus A13 B32. Okay, this index in the mid gets repeated 2. Okay, this is what you get. Fine. Is this clear to all of you? Did you understand? Basically, because sometimes in exams what they do, not in GATE, but one time it came in engineering services and one time it came in BRC maths. It was there till last year. So there they have represented a matrix by this. Okay, so basically people who don't know this summation, they don't know what is this C, but actually if something is given in this form, that denotes it, this matrix C is obtained by multiplying A with B. Okay, that's what. Because sometimes if they just give you, let's say for example, instead of giving C equal to AB, I'll give you like a matrix C is defined such that Cij is equal to summation k equal to 1 to n, then Aik Bkj. This is what I'll give you. Okay, so if I give you, that means this actually means the product of two matrices A and B, of course. Clear? That's what. Now let's see, let us talk about some properties of this matrix. Okay, so first of all, if two matrices A m by n and B n by p are to be multiplied, of course, I mean that is to calculate AB. Okay, so to calculate AB, first point that you can say is number of multiplications needed is equal to, okay, I'll just fill the space, but let's see, number of additions required, number of additions required is equal to, now let's see, this is m into n into p, and this is m times n minus 1 into p, which is very, of course, very obvious to understand. Look, how you can decide how many multiplications you have to do, first of all. Okay, look, first of all, let me take a matrix of size m by n. Okay, so let's say a11, a12, and so on. The story goes on till am1, sorry, a1n, then a21, a22, and so on, a2n, and this comes up to am1, am2, amn. Okay, this is the m by n matrix. Now let's say if I construct a n by p matrix, n by p matrix, then let's see, ultimately the first element is going to be maybe let's say b11, b12, and so on, b1p, b21, b22. Don't worry that I'm writing too many elements, because I want you to understand. Okay, that's why bp1, sorry, n1, bn2, bnp. Okay, so this is what we have. Now when you have this matrix, ultimately one point that you know is, if you multiply a m by n with n by p, you will have a matrix of size definitely m by p, correct? You know this. That means if you have a matrix of size m by p, number of elements in that matrix is nothing but product of these two, which is m into p, correct? Now let's say if you want to calculate the first column element, okay, if you want to calculate the first column element and total number of elements here, total number of elements is equal to mp, of course. Okay, so if total number of elements is equal to mp, and if you want to calculate the first element, okay, because whatever you do for this element, same thing you are going to do for all the m into p elements, so job is same. Now to calculate this first column element, ultimately you have to multiply this row with this first column. Okay, so if you want to multiply, tell me how many multiplications you have to do. First, a11 into b11, first multiplication, a12 into b21, second multiplication, like that. Total you have n elements here and also n elements here. So total, to get this first column, first column element, you have to perform n multiplications, yes or no? Because first element into first column. Okay, so this element gives first multiplication, a12 into b21, second multiplication, a13, b31, third multiplication, and so on. This a1n into bn1 gives you total n number of multiplications, which means if you have to calculate this element, you have to do n number of multiplications, yes or no? Please type in the chat box. Correct? If you want to calculate this element, you have to perform n multiplications. 2? Yes or no? Is this clear or not? Please type in the chat box. If you want to calculate this, you should do n multiplications actually. That's what I'm telling. Okay, so for getting first element, for getting one element, you should do n multiplications. N multiplications. Okay, n multiplications. Then total you have m into p elements. So in order to calculate the complete product matrix, you should perform n into mp, which is m into n into p number of multiplications, to calculate this matrix actually. Got it? Now this is by default very easy. If you want to add three numbers, then ultimately you should do two additions. Okay, so if you want to add three numbers, you have to do two additions. So when you get this n numbers, okay, a11 into b11 is the first number, a12 into b21 is the second number, similarly a1n into bn1 is the nth number. To add this n numbers, you should ultimately do n minus 1 additions to get this element. So this element involves n minus 1 multiplications and n minus 1 n multiplications and n minus 1 additions. That's it. Okay, so to get one element, if you want to do n multiplications and n minus 1 additions, then to get this total mp elements, this value n and n minus 1 has to be multiplied with m into p. That's how you have this. Clear? These points are very important, and there is a previous gate question on this. Many gate questions actually, not one. Okay, Samiksha, basically what I'm telling is, if you want to get this first column element, you have to multiply this first row with first column, which involves n multiplications actually. Okay, that's it. Clear? See, I'm just telling you, let's say if each vector has 4 elements, okay, and if you want to dot product 2 vectors, how many multiplications you have to do totally? Let's say you have 2 vectors, each vector has 4 elements in it, and if you want to do the dot product of these 2 vectors, how many multiplications you will do? Please type in the chat box. Let's say you have A, B, C, D, E, F. If you want to do the dot product of these 2, then addition वाले में n-1 क्यों आता है? I'll tell you. Just a minute. First, let us clear the multiplication doubt. So let's say you have A, B, C, D, E, F. There are 2 vectors, each containing 3 elements, for example. Then, if you multiply these 2, if you do the dot product of these 2 vectors, then how many times you use multiplication? 3 times. Correct? You multiply 3 times, right? So now this vector has n elements and this vector has n elements. So obviously you have to do n multiplications in order to get that element. Okay. Now coming to the additions, see, if I want to add 3 numbers, I'll do 2 additions. Correct. Now to get this first column element, I have a11, b11, a12, b21, a1n, bn1. So total, you have n terms and you want to add all these things. Okay. Then to add n terms, how many additions you will do? Please tell me. There are n terms in the first term. Okay. So to add this n terms, how many additions you will perform? How many additions you will perform now? See, you have n terms. Okay. a11 into b11 is the first term. a12 into b21 is the second term. a13 into b31 is the third term. Okay. And so on. So ultimately to add this n terms, you should perform n-1 additions. Okay. And these n-1 additions are being performed to get value of single one term. So total there are m into p elements. So this m into p multiplied with this n-1 gives the total number of additions that you need to perform the multiplication of both the matrices. Clear to all? Yeah. Is this clear to all of you? Okay. Now, good. Why I have taught this point? Of course, this is a gate question. Okay, fine. There are many gate questions that on this point. Okay, they'll give you a matrix of size 3/4 and matrix of size 4/5 are multiplied. Then how many additions you have to perform, or how many multiplications you have to perform? These kind of stuff they keep on asking you. But okay, so you can have the formulas now. M and P, m into n-1 into p, whatever. Why I have taught you this is, look, I'll tell you. Properties of matrix multiplication. First, properties of matrix multiplication. Properties of matrix multiplication. Okay. So first thing that you can know is matrix multiplication need not be commutative. Need not be commutative. What's the meaning of commutative? Let's see. AB may not be equal to BA. That's why whenever you're writing like equal to BA, see, if I'm multiplying 2 real numbers x and y, I can write this as y into x. There is no objection. Okay, so x into y can be replaced with y into x, of course. But if you are doing matrix multiplication, unfortunately you cannot replace a into b with b into a again. Okay, because sometimes there exist cases where they may not be equal, of course. Okay, like for example, you can see if I multiply example, let's say a is of size 3/4 and b is of size 4/5, for example. Okay, now if this is of size 3/4 and this is of size 4/5, this implies AB exists. You can multiply A into B such that the resultant matrix AB will be of size 3/5. But forget about equality. First of all, BA does not exist. Okay, so BA does not exist. This is the symbol for does not exist. Normally this is called, you might have studied, this is the existential quantifier, and if you put a cross, that means does not exist. Okay, clear? You can see BA. If you want to calculate BA, 4/5 cross 3/4. 5 and 3 are not equal, so ultimately you cannot do that. Okay, fine. Is this clear? HTV, Manoj, Arvindan, Sagnika, Hema, Gautami, Aya, Thomas, Legend of PUBG, Sujay, 𝐂𝐨𝐿, Mukund, Labai, and I can see only these names, of course. Is this clear to all of you? That's why when you are multiplying matrices, you should be very careful. Okay, let's say for example, if I have B is equal to some C, if I multiply A here, I should definitely multiply A here. Okay, I cannot multiply A here. This is different. Okay, so if you are multiplying in the P factor, on both sides you should multiply only in the P factor position. You cannot exchange the positions. Okay, that's what. Now second point which I would like to tell you is matrix multiplication is associative. Don't feel that these points are very school level points, but why I am talking, there is some importance for this in GATE exam. Okay, that means ultimately if you have three matrices for example, and let's say matrix multiplication is feasible among them. Okay, so this definitely will be equal to A times BC. The meaning is, if I give you three matrices and if I ask you to multiply, why BA not exist? Because B is of size 4 by 5 and A is of size 3 by 4, and for matrix multiplication to hold, this two numbers should be equal. Okay, that's why BA does not exist. You cannot calculate. Okay, because you have 5 elements in the first row, but you have only 3 elements in the first column. 3 elements in the first column of the matrix. Okay, you cannot perform multiplication. Okay, now basically, if you have three matrices, if I give you three matrices A, B and C, and if I ask you to calculate A into B into C, of course, then few people, they can calculate this AB first and then multiply C to them, then you can get ABC product. Or first you can calculate BC and then you can multiply A as a P factor, then also you can get ABC. Okay, these two results will be same of course, but there is one fundamental difference and your computation time will actually change. Okay, how can this happen? Look, I'll tell you. For example, say A is of size 3 by 4, B is of size 4 by 5 and C is of size 5 by 2 for example. Okay, so let's say I have asked you to multiply three matrices. I have given those three matrices, and let's say some of you, of course, since the matrix size is 3 by 5, 3 by 4, 4 by 5, they will learn the matrices. Let's say we have a computer code. Okay, so let's say some of you are trying to write computer code. Now whenever you are writing, first you can write the algorithm in such a way, A, B gets multiplied first and then C gets multiplied to the matrix AB. Let's say you multiply A and B and you assign it some other matrix D for example, then you multiply DC, then you will get A into B into C. Or first you can multiply BC and then multiply A as P factor. The difference that comes here is, look, I'll tell you. Of course, undoubtedly AB of C will be equal to A times BC. This is 100% true. Now where comes the difference is, look, if you check the number of operations the computer has to perform, or basically you have to perform if you are doing manually, if you first multiply these two matrices, number of multiplications, how many multiplications you will get? 3 into 4, 12, 12 into 5, 60. Number of additions, if you are doing A, B first and then C, okay, the number of additions you're going to do is 3 into 4 minus 1, 3 3s are 9, 9 5s are 45. So total 105 operations is what you have to perform in order to get this product AB. Now once you get this product AB, so you have AB matrix with you, which is of size 3 by 5 and C is of size 5 by 2 of course. Okay, so this is of size 5 by 2. Clear? Now again, if you want to multiply these two matrices in order to get this ABC, number of multiplications you have to do is how many? Number of multiplications, 3 into 5, 75, 75 into, 3 into 5, 15, 15 into 2, 30. Number of additions you have to do is equal to 3 into 4, 12, 12 2s are 24. Okay, so total this is 54. That means total number of operations, for A, B of C, this is equal to, initially to get this AB you should do 105 calculations, and then after to get this product of AB with C you should do 54 more calculations. So total 159 calculations you have to perform in this method. Okay, so which means if you follow this procedure of first multiplying AB and then multiplying C, you should total perform a calculations of 159. Okay, 159 calculations is what your computer, or basically you, have to perform if you are calculating the product. Now let's see the second case. Let's say first I'm doing BC and then multiplying with this. Okay, so first of all, B is of size 4 by 5, C is of size 5 by 2. So let's see how many multiplications you have to do. Number of multiplications you have to perform is 4 5s are 20, 22s are 40. Number of additions, ultimately 32. Okay, because 4 4s are 16, 16 2s are 32. So total 72 is what you have to perform. So you have got this matrix BC, which is of size 4 by 2, and A is of size again 3 by 4, so that you have to multiply. So number of multiplications here you have to perform in order to get this is 3 4s are 12, 12 2s are 24. Number of additions is 3 3s are 9, 9 2s are 18, of course. So total 42, of course. Okay, so therefore total number of operations to be performed for calculating A of BC. If you see 72 plus 42, 114 calculations. You can see, if you see, this is 159 and that is 114, which means in this method there is almost reduction of 45 calculations, which means your computation time will be slow. I mean your computation time is actually less and your computer and your code is optimum actually. Okay, did you understand the difference? This result will never change, but before starting the coding, before deciding how to write the program, if you spend some 1-2 minutes, then definitely that could save a lot of computation time. Okay, and of course these are small matrices, so you're seeing this number is very less, only 45 calculations is what, still 45 is a big number. Okay, so 45 calculations is what you are saving here. But if you go for matrices like 100 by 100 and all, you'll be saving thousands of calculations, which greatly reduce the computation time actually. Got it? This is the reason why I have taught you these formulas on calculating how to get number of multiplications and number of additions. And of course, not only for this general knowledge, there are gate questions based on that. Okay, so that's why. So many symbols are flying. Whenever I see that love symbol flying, I get this thought of balloon in my mind. You know, helium balloons. Have you ever seen helium balloons? They fill it and leave, then they float. You know this? Have you ever held one helium balloon and stood on the ground? Yes or no? Did you ever hold one helium balloon and stand? Yes. Do you know what happens if you try to hold 1000 helium balloons and stand on the ground? Do you know what happens if you try to hold 1000 helium balloons and let's say if you want to stand? Do you know what happens? AB of C calculation is wrong. 3 4s are 12, 12 5s are 60, 3 3s are 9, 9 5s are 45, 105. Okay, AB into C. 3 5s are 15, 15 2s are 30, 3 4s are 12, 12 2s are 24. So 54, 105 plus 54, 159. Some mistake here. Kids gaming. Did I perform any mistake here in AB of C? Because multiplications 3 5s are 15, 15 2s are 30, right? Okay, so 3 into 4, 12, 12 2s are 24, 54. I think it's looking fine to me. Maybe in overlook. Is this calculation correct? This calculation is correct, right? I think there is no issue with this calculation. 159. This too. Okay. Anyone getting any different answer apart from 159? Or can you find any mistakes in this calculations? Correct, right? Yeah. Just please check the calculation once again, kids gaming. Okay. So I think that's fine. Okay. Fine. As I promised you, every day after 1 hour I'll teach you some basic stuff which is helpful to you. Okay. So it's already 1 hour, 7:55, roughly 55 minutes already it's been. So it's okay. Hey, you need not be sorry here. I have committed a lot of calculation mistakes in my life. Okay. I have told you the consequences also correct. 2 times I missed All India rank 1. It happens. Okay. So no, don't worry. But please make sure you don't commit in exam. Okay. Then let's see. I'll do some sequence of steps. Try to identify what is the mistake. Is it total English class? Yes, of course. Okay. Now let's see. I'm taking 2 numbers. Okay. Then let's say if I write yes, AB equal to B square. Okay. So because A equal to B, and if I multiply B on both sides, you can have AB equal to B square, of course. Okay. Then let's do one more thing. I'm subtracting both terms from A square. Okay. Since AB and B square are same. So if I subtract AB from A square or B square from A square, it is same. If I take A common, you have A minus B, and this, you know, it can be written as A minus B into A plus B, of course. So then I'm cancelling this common factor maybe. So A is equal to A plus B. So since A and B both are same, I'm replacing this B with A again. I'm telling A is not equal to 0 and B is also not equal to 0. I am cancelling A. So this is what I have. Okay, 1 is equal to 2. Clear? Now, and ultimately we know 1 is not equal to 2, of course, that's 2. What is the mistake in this? Let's say, for example, if I write the step numbers, 1, of course 1 is assumption, so I'm just leaving 1, 2, 3, 4, 5, 6, 7. So in this 7 steps, where is the mistake? Because ultimately, you know, this is not 2. Okay, so this is not correct ultimately. Where is the mistake? Violating rules, huh? Always crossing the lines gives you some fun in life. Okay, no mistake. Then why it is mistake? No, 1 equal to 2. If 1 equal to 2, job is very easier. You know, you write any number in exam, you can equate it. So आपका exercise कब लेके आओगे? Not before July, क्योंकि schedule per packed है. Somesh, 6th step. Okay, 6th step I have done some mistake. What is the mistake in the 6th step? Somesh, you might be correct. Okay, so what is the mistake in the 6th step I have done? Third step, 1, 2, 3. Okay, Sagnika want to say it's third step. Somesh want to say it's 6th step. Fine. Okay, since Somesh has commented first, what is the mistake in 6th step? What do you feel is the mistake in the 6th step that I have committed? Since I'm asking to tell one step number, some of you are telling some numbers, huh? No. What is the mistake in the 6th step? Think for a while. In 6th step, we should not cancel. Why? Why I should not cancel in 6th step? B is not has been used. Okay, if you want, since A equal to B, I'll replace B's, both A's with B. Then also you'll get 1 equal to 2. That doesn't change. Let's say you're in interview and someone asked you this. Okay, why? Everything is correct mathematically. I'm getting 1 equal to 2, but you know 1 is not equal to 2. Then why? I have full rights to cancel A because A is not equal to 0. And by the way, Sagnika, that's correct. You actually told the answer. This is the step that has mistake in it. In this step, cancellation cannot be done. Okay, yeah, third step, correct. Cancellation cannot be done. The reason is I have actually given you hint. I thought some of you will say, of course, Sagnika and 𝐂𝐸𝐬𝐿 has told. Good. So basically, I've written these two numbers to give you hint actually. Okay, you see, in the beginning I have not written these numbers, but later I have written to give you hint. When I am cancelling this A's, I told A should not be equal to 0, correct? But if A is exactly equal to B, this A minus B is equal to 0. I cannot cancel 2 zeros. If I can cancel 2 zeros, I can do wonders. Okay, like 0 equal to 0, 2, 3 into 0 equal to say 9099 into 0 into 9 into 0. I'll cancel 0 and say 3 equal to 9999. In fact, I can say any two numbers are equal in this world. Okay, then there is nothing comparison. Life will be happy for us, correct? So basically you cannot cancel 2 zeros, and you can see this is cancellation of 2 zeros. Okay, here cancellation cannot be done because when A is equal to B, this implies A minus B is equal to 0. Okay, that's what. Clear? Fine? Happy? Okay, so 2 zeros cannot be cancelled actually. But can I ask you one question, of course, which we will deal in the next chapter, basic calculus. You might have seen these things. I'm sure you might have done these kind of things in your life. Have you done this anytime? Have you done this anytime? 2 plus 2 equal to 4. Of course, you might have done. Okay, if I, or else without doing this business, if I ask you what is the limit of, what is this limit, you will say 4. Of course, many of you will say 4. Even I would say 4. Okay. Now there is a conflict here. Here you are telling 2 zeros cannot be cancelled. Fine. Okay. Then how you are cancelling here? Okay, let's say if you say x minus 2 is not equal to 0 in this case, then why you are putting x equal to 2 again in this? Did you understand? If you look at this slide, whatever I have done, this part, whatever I have done in this big portion, you can clearly understand 2 zeros can never be cancelled. Good, fine. Okay, I cannot cancel 2 zeros because you have seen if I can cancel 2 zeros, a lot of wonders we can do. That should not be done. Then if you are doing this calculation, then ultimately you will cancel this x minus 2, which is allowed legally, of course. So this x minus 2, if you cancel, that means in one way you are telling that this x minus 2 is not equal to 0 because you are cancelling actually. Okay, so okay, fine, x minus 2 is not equal to 0, fine, which means you are clearly 100% sure that x is not equal to 2. Good, that's what na, x minus 2 not equal to 0. This ultimately tells you the final thing, x is not equal to 2. Fair enough. Then if x is not equal to 2, in the next step, how you are putting this x as 2 here? That's the question. And how you are telling answer as 4? That's the question. Understood? Did you understand? Are you all understanding or not here? Please type in the chat box something. At least type some movie title here. कुछ समझ में नहीं आई है वैसा. No. Yes. X is tends to 2. No. Yes. X is tending towards 2, not exactly 2. Then why you are putting exactly 2 here? That's my question. I understand your concern. You want to tell me x is not equal to 2. Fine, I agree. Okay, because you are cancelling. Then why you are putting x equal to 2 here again? You are putting exactly 2 in fact. Okay, to get the value of limit. We are finding value of function when x tends to 2. Good. Fine. We'll see what is this when we come to the limits, hopefully in the next Monday. Okay. Clear to all of you? Yes or no? First of all, did you understand the question? Why it's at some point we are telling x is not equal to 2, again at some point why we are telling x equal to 2. We'll see what is all this stuff. But did you all understand what is the question that I'm asking you? If you understand the question, that's fine. We'll see what is the answer in the next week. Okay, when we start basic calculus, no issue. But is this clear to all of you? Yes? These kind of things make you think a lot. Okay? Fine. Now I think half of you are thinking this fellow should not teach maths, making maths very complicated. We are happy with life, cancelling all the stuff, putting x equal to 2 and living peacefully, and now this fellow is coming and telling all these things. Correct? How many of you are feeling this? I'm telling you now. See, I'm just telling you guys one thing. Correct? You might have felt that, no? Unnecessarily making life complicated. I'm happy with solving PYQs. I'm getting good enough answers. My life was happy. Parents bought me iPhone also when I have shown them the test series marks. But then I'm telling you, see, if just clearing gate is the business, na, 1 week or maximum 2 weeks is completely enough for me to teach maths. Okay, I'll teach you questions, you'll get answers. In fact, that's what we do now in the fast track or Maha-revisions. When gate is just 1 or 2 weeks down the line, 4 is not the answer, isn't it, sir? It is close to 4, maybe more or little less. It is equal to 4 as long as I write this, not this, in fact, as long as I write this. Okay, we'll see what why that can be written and all. You can write this is equal to sign only if you write this. Okay, if there is no limit, you cannot put equal to. That's the main idea. But anyway, let's see. See what I'm telling now. If I just want to make you get good marks in maths in gate examination or whatever, I'm telling you just 2 weeks is good enough for me to teach maths. Okay, in fact, I can teach in a single day also. I'll just put the title Maha-revision on the board and clear the stuff. Okay, but the fact is, when you go for any interview, see, there are many few things which directly give you something based on your gate score. Okay, let's say for example you got DRDO. Okay, let's say if you want to join DRDO, okay, or any PSU in general, hardly you can count the number of PSUs which gives the direct offer based on gate score. Okay, many PSUs they have interviews, and almost many IITs and IISc they have interviews. Okay, IISc is only one of course, but in many branches in IISc you have interviews for MTech admission. Okay, so if you go to departments like ISRO, DRDO or BRC place where I was there in the past, so if you go to these things, definitely you will have to know maths. Okay, because let's say for example if you go to some interview, okay, or if you get placed in any company, people never expect you to sit there and derive and write what is Newton's law of motion. Then it's not like you write the rate of change of momentum of a body. People never expect this. Okay, they want you to design, to analyze things. Okay, mathematically you should say, let's say for example if I'm filling a tank of petrol, okay, then you should do some analysis and should tell at what time, by what time this tank gets filled actually. Okay, you should say this. And many people they just say discharge divided by velocity gives the time for filling, but no. Okay, because the time it takes, let's say for example there's a pipeline, initially when the tank is empty, then the time reached by the fluid to reach from the ending of the tank to touch the tank will from the position ending of the tap or the pipe to touch that tank will be large. But let's say if the fluid is keeping filled, then by the time it comes up, then ultimately the distance reduces, and you know the filling will be soon than what you have expected. So let's say now you have done the calculation and thought it will take 40 minutes for it to fill, so I'll go for a coffee, and you are chilling in the canteen, and let's say after 37 minutes the tank got filled and let's say petrol got spilled out. Okay, then what you will do? You'll be in trouble. Okay, so all these things you should be little careful. You're master of fluid mechanics. Thank you. I'm master of many things. Okay, except cracking some good jokes. I'm very bad at that. But anyway, this class will be slightly boring, but please get adjusted. At least you will get marks and you'll smile in the last. Okay, at least maybe not in the classes. Fine, so let's get back to our matrix story then. So basically, yeah, this is the ultimate point what I want to discuss. The number of operations, if you see, there's a huge difference of 45 operations, which is almost like 1/3 of this value. Okay, so that's what I'm telling. Whenever the matrix size is big, the difference in these operations will be very large. So before starting the coding or something, you just perform this analysis for 1-2 minutes. That could save a lot of computation time. Okay, so this is the ultimate thing. Now let's see one more thing. How many points I told, by the way? 2 points. Yeah, couple of points I've told. Now let's see product of two non-zero matrices can be a zero matrix or a null matrix. Null matrix. Okay, so let's see. You can easily find out, because we have this analogy. If product of two real numbers is 0, then ultimately you're habituated to write x equal to 0 or y equal to 0. But in matrices it is quite possible that even if these two are non-zeros, still this can hold. Okay, I'll show you with an example. Maybe you will get clearly. Let's say if I have this matrix A 0 0 0. Okay, it is non-zero clearly. Okay, let's put the element 2 for example. Okay, because this is non-zero. Then B equal to 0 0 0 minus 4. So let's say I have taken this matrix. Then ultimately these two are not null matrices, because we have at least one non-zero element. Okay, but if you multiply this AB, you'll understand something. If you multiply this AB, 2 into 0 plus 0 into 0 0, 2 into 0 plus 0 into minus 4 0. These two are zeros, so ultimately these things will be zeros. Okay, so AB is equal to 0. So they can ask you if product of two matrices, they'll ask you, can product of two non-zero matrices can be a zero matrix? People generally tend to say no, because both the matrices are non-zero, so when you multiply you'll get something. Okay, but you can have a zero matrix as per this. Clear? Then let's see few more points of matrix multiplication. 4. Well, trace of AB, if you have for example multiplication feasible, then that's definitely equal to trace of BA if both AB and BA exist. And BA exist actually. Okay, You can actually tell this very easily. See, for example, Cij is equal to summation I equal to 1 to k 1 to n a I k b, sorry, this is k equal to 1, not I equal to 1, k equal to 1 to n b kj. This is what you told. Okay, now let's say if I want to calculate trace of these elements, okay, like for example this is Cij element. If you're multiplying a and b, capital A and capital B, then any element in C is given by this form, you know. Now trace of this matrix is nothing but trace of C is nothing but Cij when I and j both are equal, actually, correct? Yes or no? Can you understand? If I want to calculate trace of C, that tells me actually, let's say for example if I give some other number CSS, for example, okay, so S is the number, some numbers here PQ maybe, okay, but P should be equal to Q, okay, if I want to calculate trace sum of all the diagonal elements. Now when these two are equal means if I flip I and j, the things do not change actually, okay, the total summation will not change. If you want you can take it 2 by 2 and you can check the total summation what you get after the expansion will not change, okay, that's it. Then trace of this multiplication will not change if the matrix multiplication exists. Then let us see some properties of transpose. You have AB whole transpose. If you transpose the multiplication of two matrices actually, okay, so this gives you B transpose multiplied with A transpose, of course, okay. So if you have this AB and if you do the transpose of this matrix, then you will have B transpose into A transpose. Again this can be shown easily. Cij is equal to k equal to 1 to n A I k B k j. Then if you do the transpose, this element becomes Ji, okay, Ji. So then if you swap these two, then definitely this becomes B I k A k j. That tells you this B and A got multiplied but with the transpose symbols, okay. So anyway you can just try all these things, because initial notations again I don't want to go in depth, some of you may not be very familiar. So trace is equal to all diagonal elements. Why not A transpose into B transpose? The reason is, look, I can tell you, let's say you are multiplying AB for example, okay, and this is of size 3 by 4 and this is of size 4 by 5. Then if you calculate AB, this is of size 3 by 5, and by the time you put transpose, this is of size 5 by 3, of course, okay. Now if you do A transpose into B transpose, let's see what happens. Does not exist, okay, but if you do B transpose A transpose, this B transpose will give you 5 by 4, A transpose gives you 4 by 3, and finally you will get this as 5 by 3, which is this, okay. See, if you doubt some point, just take two matrices and check the conditions in exam also, okay. It's not like you don't have it in the notes or something. Of course I'll try to teach, because promisely not only me, even if the legends of maths actually come, they cannot teach complete maths in a single you know, episode or single book or single anything, okay. So I'm just trying to cover the GATE syllabus and the things which connects all the GATE PYQs, okay. So this is what you have, clear? You can check this do not valid, it's not valid, okay. Then also sixth point, if I want to say, if you generalize this A B C D whole transpose, this comes up D transpose C transpose B transpose A transpose in the same order of multiplication, okay. So all this is basic stuff. Now let me ask you one question. I'll give you a question, I'll set the poll. Now you know some properties, so please answer this question. I'm giving you, okay, for previous question what is the answer? I have asked you 5,31,114 something, okay, fine, but I am sure none of you might have typed that. So single choice, 60 seconds I'm giving, start. Come on, enter in the chat box. I'll just have some water and come back. Solve this question. If A is a matrix, square matrix, of course a real square matrix, fine. A into A transpose is, what is A into A transpose? Unsymmetric means some random matrix, sometimes symmetric, always symmetric, skew symmetric. Come on, C always symmetric. Okay, maybe B sometimes symmetric. Okay, you have still some time to think. All of you can think. Piyush wanna say it's always symmetric. Okay, B, C. Okay, the fight is between B and C. Let me resolve the tie then. Okay, so let's see. As I told you, if you want to check symmetricness of any matrix, okay, let B is equal to this matrix A into A transpose. Whatever you want to check, so make that matrix as B. Now, if you want to check something is symmetric, what you'll do? Consider the transpose of that and check whether the transpose is giving the same matrix or not again. Okay, so if you consider, this implies B transpose is equal to A into A transpose whole transpose. Okay, so this gives you, this is product of two matrices, so B transpose into A transpose, this is what you get. And if you transpose even number of times, you'll get A into A transpose. This is same as B again. Okay, so this implies B transpose is equal to B. So therefore B, which is A transpose, is always symmetric. This is also a gate question actually. They'll ask you this kind of stuff. Okay, so you can just check it up for some time and just tell. See, if you just want to verify any matrix, let's say for example, if I give you some matrix, okay, and if I ask you whether let's say if I give you A square plus the A whatever, and if I ask you whether this matrix is symmetric, then just consider that matrix as B or C whatever, then consider the transpose of that. Using simple properties of transpose, try to simplify that. If you are again getting the same matrix, it's symmetric. If you are getting negative of that matrix, it is skew symmetric. If you are getting none out of them, then ultimately it's some random matrix. Okay, this is how you should figure out. Then let me give you few things which would be helpful to you. These are also gate questions actually, but I just want to give you. If A and B are symmetric matrices, then AB plus BA is always symmetric. AB minus BA is always skew symmetric. Is always skew symmetric. Okay, is always skew symmetric. So how do you know this? Just mug up. Okay, fine, clear. So mug up these 2 points very well so that you can get good marks in exam. Fine. Yes or no? No. Yes. There are some people who are thinking, sir, mugging up is my art since childhood. I can mug up, no issue. Okay. People are feeling this now? No. Look, I'll tell you. See here. Basically, whatever the combinations they give you, the procedure is same. Take that matrix as no mug up, sir. Good. Okay. Fine. So let's see how we can actually show them. So A given. Okay. First of all, they have given you A and B are symmetric matrices. So undoubtedly A equal to A transpose and B equal to B transpose, of course. Okay. Then, so first let us look at AB plus BA and see whether it is symmetric or not. Okay. So 1 or A, let C is equal to AB plus BA, and you want to check what is the nature of this matrix. Okay. Then let us consider C transpose. That gives you AB plus BA whole transpose, which gives you AB whole transpose plus BA whole transpose. Then this is product of two matrices, so I can write B transpose into A transpose plus A transpose into B transpose, which is equal to BA. Why I can write BA? Because A and B are symmetric. If I have B transpose, I can replace with B. A transpose I can replace with A, plus A transpose can be replaced with A and B transpose can be replaced with B. Now matrix multiplication may not be commutative, but matrix addition is commutative. Means if you add two matrices in any form, they are always equal. Okay. So if you have BA plus AB, if I bring these two terms here, if I exchange these two terms, I'll have AB plus BA, which is equal to C again. Okay, so you can see by applying simple properties of matrix addition and multiplication, you found out C transpose is again equal to C. Guys, please remember one point. I'm not changing this BA as AB, okay, because I don't know whether these matrices may commute in multiplication or not. Okay, so let the mind think more. You should think. Okay, so this BA is not replaced with AB. Okay, I'm writing this step because I'm exchanging these two terms in addition. Okay, not this swapping in multiplication. Clear? Because there could be students who may feel that I'm swapping these two, but that's not the case actually. Okay, fine. Is this clear to all of you? Are you getting these points or not? I'm not swapping these two because I'm not computing multiplication. Transpose of a matrix give matrix itself, thus symmetric. Yeah, of course. Okay, so this is equal to C. Therefore, since C transpose is equal to C, this implies C, which is equal to AB plus BA, is symmetric. Is symmetric. Now I'll give you some point. Please think a bit and try to show that this is skew symmetric. Actually, this is skew symmetric. So please try to show this. This is skew symmetric. You can try. Okay, if it's an offline class, I would have come to your books and checked whether you are trying or not. Okay, so let's see. B. Let C is equal to AB minus BA, which implies C transpose is equal to, again the same story, AB minus BA whole transpose. This gives you AB whole transpose minus BA whole transpose. So this gives you B transpose A transpose minus A transpose B transpose. So BA, because these are symmetric, minus AB. So if you take a minus sign, you'll have AB minus BA, which is equal to minus C. So therefore C is skew symmetric. C is skew symmetric. Checking. Okay, good. Fine. Okay, so C is skew symmetric. Now whatever they give you, if let's say instead of giving symmetric, they have told you it is skew symmetric, then what you will do? Ultimately you will replace, the same results do come. The reason is, here you will have B transpose A transpose, you will replace with minus B and minus A. Minus into minus again gives you BA. Okay, if this is minus A into minus B, then again it gives you AB. Similarly here, the signs do not change. Okay, so if they are symmetric or skew symmetric, it doesn't matter. These things will always remain symmetric and skew symmetric. Okay, clear? Aya, Ramu, Thomas, Hrishnan, Sagnika, Abdul, Kids Gaming, Hrishnan, Thomas, Surya Prasad, Labbai, all of you. Okay, fine. So let's solve one more question. Solve this question. I'm again conducting poll, of course. Why not A transpose B transpose? I have told, I have answered. Good. So for previous question, the correct answer is C. So I hope 66.67. Abdul, Piyush, you guys have answered. Okay. Now new poll. For this, I'm giving 60 seconds again, or maybe 90 seconds if you want to perform calculations. Do. So for these type of questions, we have to go for transpose. Ultimately, if they are asking you whether the symmetric check or skew symmetric check, you should go for transpose. Okay, common funda. The matrices cos minus sin sin cos A0 0 B commute under multiplication if one of these things happen. Okay, so what are they? Commute means if you multiply this and this, or first this and then this as post factor, it doesn't matter. Okay, so they should commute under multiplication. So under what case they'll commute in multiplication? That's the question. Come on, solve this. Okay, Mohan is telling C. Again you want to say B. Okay, always or never? B or C? B. Always. Okay, always A. Manoj want to say it's A. Okay, let's see. Okay, so let's see. First of all, if they want to commute under multiplication, cos minus sin theta, cos theta into 𝐂𝐳𝐤𝐬b. This should be same as 𝐂𝐳𝐤𝐬b cos minus sin theta and cos theta. So now if you simplify this, ultimately this is 2 by 2, 2 by 2, so we'll have a 2 by 2 matrix. Okay, so let's see. First element would be A cos theta. Okay, because cos theta into A minus sin theta into 0, you have 0. Cos theta into 0 plus minus sin theta into B, this is minus B sin theta. Similarly, you have A sin theta, B cos theta. Now coming here, you have A cos theta, 0 into sin theta, A into minus sin theta, so minus A sin theta, 0 into cos theta plus B sin theta, B cos theta. Okay, so this is what you have. Now these two matrices has to be equal. They are asking you, okay, D also got covered. Good. Now all the 4 options got covered. We'll see what is the actual option. Look, see here, if these two matrices has to be equal, then ultimately sizes should be equal. Yeah, of course, they both are of size 2 by 2. Then at the same time, corresponding elements has to be same. Okay, so which means A cos theta and A cos theta has to be same. Ultimately, whatever the value of A you keep and whatever the value of theta you substitute, these two will be always equal because they are same terms. Okay, then minus B sin theta should be equal to minus A sin theta. That means minus B sin theta should be equal to A sin theta minus A sin theta. This tells you A minus B times of sin theta is equal to 0. Okay, this is one possibility. Then again, A sin theta should be equal to B sin theta. A sin theta should be equal to B sin theta. Again the same thing. This condition will also lead to the same condition. Then B cos theta and B cos theta will be equal at any values of B and theta, no issue. Now the main thing is, if these two matrices has to commute in multiplication, ultimately A minus B times of sin theta has to be 0, right? If this has to be 0, this implies this is a scalar. Okay, so A minus B has to be 0 or sin theta should be 0. Actually, this implies your A should be equal to B or theta should be equal to n pi, of course. Okay, because you know sin theta is 0 only when theta is integral multiple of pi. So theta is equal to n times of pi, where n is some integer. Okay, 0, 1, 2, 3, minus 1, minus 2, whatever. Then if this happens, then ultimately these two matrices are equal. If this do not happen, these two are not equal, because if I put a not equal to sign here, that means these two elements are not same, and obviously these two elements are also not same. Okay, so therefore either A should be equal to B or theta should be equal to n pi if this matrices has to commute under multiplication. Okay, so therefore A is actually the correct answer. Okay, got it? Yes or no? Actually guys, you will see what is the physical significance of this a bit later. Okay, so this actually tells you about one very beautiful thing actually. Okay, I just will say now. Okay, now itself I'll tell you. Look, if you take this matrix cos theta minus sin theta whatever, look, okay, fine, we'll see some special matrices now. See, in yesterday's class I have told skew symmetric matrix, correct? What is the number I have given there in types of matrices? Of course, we are dealing matrix algebra also together. Matrix algebra and types of matrices combinedly we are dealing. For skew symmetric matrix, what is the number I have given? Types of matrices. Okay, so I'm following some sequence, right? So what is the number I have given there in the last class? No idea. I just turned pages here. Book already given to Bajji wala, Pani Puri wala. No, 7. Okay, so let's say 8. Orthogonal matrix. Orthogonal matrix. Okay, 7 skew symmetric. Okay, fine, good. So 8 orthogonal matrix. So do anyone know what is an orthogonal matrix? First of all, do anyone of you know what is an orthogonal matrix? It's a very powerful matrix actually. Okay, what is an orthogonal matrix? A equal to A, sorry, A transpose equal to A inverse. Okay, good. Maybe. Yeah, okay, yeah, it's true. A transpose equal to A inverse. Yeah, correct. Any other thing? Yeah, what you told is correct, Abdul. But I just want to know if someone knows something else about this. A transpose equal to identity. A into A transpose equal to I. Of course, yeah, okay. Basically the same thing. You're just interchanging. A into A transpose equal to A ultimately means A transpose equal to A inverse, of course. Det A equal to 0. No. Determinant of an orthogonal matrix is never 0. I'm 100% sure. Determinant of an orthogonal matrix will never be 0. I'm 100% sure of it. Rank, okay. If determinant is not 0, then ultimately rank will be maximum, I mean equal to size of the matrix. That's connected. Anyway, let's see. First of all, before telling orthogonal matrix, I just want to give you some basic idea about matrix multiplications. So let's see. I'll just deal in 2D so that you can understand things better. If you have a matrix, say A equal to 1, 2, maybe 3, 1, let's say some 2 by 2 matrix. Now let's say you all might have studied this at least in class 11 or diploma first year. Origin x, y. So let's say you have some vector. Say this vector is 0.1, 2, which means I plus j. So if you write in matrix form, let's say this vector is A bar. So A, I'm writing it as 1, 2. Okay, so I'm writing it as 1, 2. So ultimately, you know, this vector can be replaced with this coordinates 1, 2. So I'm just writing this as elements 1, 2. Okay, or this is some vector x, for example. Let's change the name because A we are using here already. So x is this vector. Now, whenever you multiply two vectors, dot product of two vectors is 0. We'll see. Okay, what happens, we'll see. So first of all, if I ask you to calculate AA or AX, for example, okay, x is this vector, and let's say if I want you to calculate A into x, then you will definitely tell me the answer is 1, 2, 3, 1. You multiply with 1, 2, then ultimately you will get 1 plus 4, 5, 3 plus 2. What is 3 plus 2? 1 plus 5 is 5, 3 plus 2 is also 5. Good. 5, 5. Okay, so this is coming out to be 5, 5. Now what does this 5, 5 tells you actually? Okay, the matrix which is like this, if you operate this matrix on this vector, this is initially the vector which is x 1, 2. Now let's say you call this as some y equal to x. Ultimately you will get a vector again. If you operate any tensor, okay, if you operate any matrix on any vector, you will get one more vector. You know this. Now let's see this vector. If you plot, this is 5, 5. Of course, I'm not drawing as per the scale. 5 will go very far because 1 is 1 here itself. But let's say this is 5, 5. This is 5, 5. Of course, you can clearly understand one thing. When you apply this matrix on this vector, that matrix has actually stretched the vector. Its length got increased. At the same time, this matrix has also rotated this vector. Yes or no? Correct? Can you understand? If I apply this matrix on this vector, this matrix has actually stretched this vector, and also it has rotated that vector by some angle theta. Okay, so let's say this angle is theta maybe. So it has got some rotation theta. We'll see how to figure out that. You can easily calculate because you know this vector, you know this vector. You can calculate angle between them. It's very easy, no issues. But main thing is this matrix has stretched it and also rotated it. Okay. Similarly, any matrix can actually perform any transformation like stretching, rotation. Normally vector is classified by its length, magnitude, and direction. Okay. So whenever you apply a matrix on a actually they're called tensors, of course. Okay, but for this purpose of the class, let's call that matrix. Okay. So if you apply this matrix on the vector, you will see there is change in length and magnitude of this vector. Okay. Now there are some special cases where this matrices will only be able to change the length of the vector but not the direction. Okay, means let's say for example, if you calculate, okay, okay, fine, we'll deal this later because I just want to teach one more concept in order to get there. There could be anything that this matrix can do to this vector. In some cases, this matrix can only stretch this vector but not rotate this. In some cases, this can only rotate but it will not stretch, means length remains same actually here. Okay, so let us see, x vector will be above, this is y, sorry, this is y. Okay, 5 comma 5. Now let's understand something about this orthogonal matrix. The matrix that preserves length of the vector. Length of any vector. Length of any vector. It produces only rotation. Okay, I'll just give you an example. A is equal to, you take for example this example only, cos theta minus sin theta and cos theta. Okay, you take this. Let's take for example, for some time, let's take this values as elements. So let's say theta equal to 90, 0, minus 1, 1, 0 for example. This is some matrix, okay, what I have taken. If you take this matrix and if you multiply any vector with this matrix, ultimately the length of the vector will not change. I'll show you. See. So again you take maybe this vector 1 comma 2, whatever. One comma 2. I'll also show you so many beautiful points. Sir, can't we write that vector as row matrix? Should it be always column vector? Just to make the matrix multiplication feasible, I'm writing it as column matrix. That's it. Okay. Normally, if the only representation is the business, you can represent either using column or this row. But generally, columns are classically followed because they're operated by matrices. In order to facilitate the matrix multiplication, we'll just write it as column matrix. That's it. Okay. Nothing big stuff in that. So let's see. If this is your x vector, of course, then if you calculate this ax, for example, so 0, minus 1, 1, 0. In fact, you will also see what comes as the answer. In fact, I know the answer. It comes as 2 comma minus 1. Yeah, of course, it comes out as 2 comma minus 2 comma 1, of course. So anyway, let's see how this happens. If you do it 1 and 2, this value turns up to be 0 into 1 and minus 1 into 2. So this is minus 2. 1 into 1 and 0 into 2, this is 1, of course. Okay, so minus 2 comma 1 is what you're getting. Okay, so if you plot this vector, you can understand something very nice understanding. This is the vector which is minus 2 comma 1, of course, and this is your y, let's say. This is the matrix which is obtained by multiplying these two matrices. Okay, and this is y, of course. Can anyone tell me if this is 𝐂𝐨𝐮? Okay, I have marked already. This is 𝐂𝐨𝐮. Can anyone tell me what is the angle between these two vectors? Can anyone tell me what is the angle between these two vectors? Can anyone tell me what is the angle between those two vectors? This is I plus j, I plus 2j. This is minus 2i plus j, let's say. What is the angle between two vectors? If two vectors are given, you know how to calculate angle, no? You know or don't know? It's okay. If you don't know, I'll teach you, no issues. It's 90, correct? 90. So you can understand one thing, this angle is 90. At the same time, if you check, definitely mod of x will be equal to mod of y, because you can check root of 1 square plus 2 square is same as root of minus 2 whole square plus 1 square. Okay, length did not change. Clear? You can see that this length, and when you basically operate this matrix on this vector, the length did not change. Okay, and this matrix of such form is basically called the orthogonal matrix, and it should not be like only for a few vectors. You take any vector, definitely length should be preserved. Let's say instead of using 1 2, if I replace 3 4, then I get minus 4 comma 3. Okay, basically a line which is perpendicular. The reason why I'm getting 90 degrees rotation is because the general form is the orthogonal matrix doesn't change length, it produces pure rotation. It produces pure rotation actually. Okay, and the reason why you are getting 90 degrees change here is because to rotate a vector x in 2D, I'm taking, of course, a vector x. So let's say in 2D I'm talking, because geometrically it's easy to discuss. So to rotate a vector x by an angle theta, the transformation matrix is A is equal to cos theta minus sin theta anti-clockwise. Okay, so this is anti-clockwise because that's the general convention when you develop this matrix, sin theta cos theta. Okay, so since if I put theta equal to 90 in this matrix, exactly this is the matrix what I can generate. Yes or no? Because if I put theta equal to 90, 0 minus 1 1 0 0 minus 1 1 0. Okay, so that's why since I have taken theta equal to 90, I know the answer. Before doing this calculation I know the answer. This matrix will rotate this vector by 90 degrees in the anti-clockwise direction, which exactly is what you got. Okay, is this clear? Yes or no? If you multiply any matrix with orthogonal, we get rotation only. Is this correct? Yes, 100%. It never changes the length. Clear? Yes or no? Now, one more point. You can check one thing. Why this name orthogonal? Okay, because in this case, of course, this is special case of theta equal to 90, but in general, let's say if I take theta equal to 30, still this is an orthogonal matrix. Why this name orthogonal come here? Okay, it's not because this always rotates by 90, but in this matrix, the general form, you multiply any two rows or any two columns, you will get definite, means if you take this as vectors, okay, means if you multiply these two columns, okay, means this you take as one vector and this you take as one vector and you take dot product, or you take this row and this row and you do the dot product of both those, you will definitely get 0. Got it? सर मैं मैथ्स में कैलकुलस वाला पोर्शन काफ़ी वीक है सर, मुझे बेसिक पढ़ना पड़ेगा या क्लास सफिशिएंट हो गए क्योंकि मैं पूरा बेसिक से स्टार्ट करता हूँ. ओके, जैसे मैंने मैट्रिक्स का डेफिनेशन से स्टार्ट किया था वैसा ही स्टार्ट करता हूँ. ओके, नो इश्यूज, बट आई विल टीच इन इंग्लिश. ओके, because there are many other students and this batch is exclusively dedicated for English understanding students, so I'll be teaching complete content in English. Okay, yes, so let's see. You can check if I take dot product of any two rows or any two columns, I'll get 0 definitely. You can try cos theta into sin theta minus sin theta into cos theta, they cancel up. Cos theta into minus sin theta into cos theta, they again cancel up. Okay, so in 3D you have this matrix as cos sin 0 minus sin theta cos theta 0 0 0 1 actually here. You can actually prove all these things, but it's okay, no issue. So cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 actually here. Okay, now so that's why it's called orthogonal matrix, because if you every two rows or any two columns are basically orthogonal. Okay, so you take in this 3 by 3, you take any two columns or any two rows or any basically, and if you do the dot product you will end up with zeros. Okay, now one thing I just want to say, look here, you know one thing, if q times x is equal to y, of course, okay, q times x is equal to y undoubtedly, then okay, since I did not teach you determinants, I'll teach this concept later. So one more understanding of this way is, look, if you do transpose of this matrix, okay, so we have ax is equal to y, of course. Okay, ax is equal to y, and you know length will not change. But you know one thing, this a will just perform a rotation of theta. Now I'll ask you one question. If you, for example, take transpose, okay, so if you take a transpose, okay, which is equal to similarly cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, of course. Okay, so this is what you have. Can I tell you one thing? Can I ask you one thing? This matrix whatever I got here is nothing but, if I replace theta with minus theta in this matrix, this is what I'm going to get. Yes or no? Can you understand? I'm repeating, please tell me. If I transpose of this matrix, mathematically what I observe is, instead of putting thetas in this place, if I keep minus theta, means instead of rotating the vector anti-clockwise, if I want to rotate clockwise, then this is what the matrix I want to use. Correct? Will you all agree with me? If I put theta equal to minus theta, then that's the matrix what I'm going to get. Correct? Because this minus sine of minus theta gives me minus sine theta, minus of sine of minus theta gives me minus of minus sine theta, which is actually sine theta. Okay? Now, try to understand one thing, guys. If you have a matrix, okay, if you have a coordinate system, of course, 0, x, y, and let's say I'm putting some vector this way. This is maybe my x. My x means not ex, this is x. Okay, so this is x bar. Now, let's see. First of all, if I take an orthogonal matrix, let's say for example A is my orthogonal matrix. Okay, I have applied this x, I am going to get y. Ultimately, this will perform some rotation. Let's say this is some angle theta, so some angle rotation it has performed such that its length do not change. But one thing that you have observed is it has rotated by an angle theta. Okay, it has rotated anti-clockwise by an angle theta. Okay, so this is my y. This is my y, of course. You know this. Now, if I apply a transpose on y, can anyone tell me what will I get again? A transpose is nothing but rotation in the clockwise sense. Okay, so if rotation is in the clockwise sense, and if I rotate y clockwise by theta, then can anyone tell me what I'll get here again? What I'll get here again? Can anyone tell me this? If I apply y A transpose on y, what I'll get here? Basically, this A transpose will rotate this y clockwise by theta. Okay, if I rotate y clockwise by theta, again what I'll get? What I'll get? X. Correct? You'll again get x. So the rotation back will again give you x. That means if you take a orthogonal matrix and if you operate first with the matrix and then with its transpose, you will again get the same thing. That means transpose operation is just like an inverse operation. Understood? So first I'm applying matrix A and I'm rotating this, then again I'm applying A transpose, I'm getting it back. That means applying transpose is so we know that A transpose equal to I is the basic definition of orthogonal matrix, or it is just another property. You're seeing, no? Why A transpose equal to I? A transpose equal to I is one of the property being exhibited by this matrix because length is not being changed. Understood? Clear? Are you all getting things? This A into A transpose equal to I is one of the things which is coming out as consequence of not changing the length. Understood? And because of this thing. Clear? So that means this transpose operation will again give you x, of course. Okay, so clearly you can see if you apply A on both sides, for example, let's say if I multiply this matrix both sides with A, it tells you A into A transpose operating on y is equal to this Ax is again y. So ultimately this term which is here should be identity matrix. Otherwise, if this is not identity, y will not give y always. Okay, so we can extend it to any general matrix. Yes. So how A transpose multiplication gives again x? You want to check? Fine. Example, you take this. Okay, so A transpose 0 minus 1. Okay, 0 1 minus 1 0. This is A transpose, and y is minus 2 1. If you do this, you will again get 1 2, which is this initially. Understood? Did you all understand these things or not? Please tell me very clearly. If you didn't understand, I'll do something to make you understand. Okay, but please don't just simply accept because I'm teaching. Are you all understanding? Did you all understand how this is happening? When you apply this matrix on some vector, you're getting y. If you are applying transpose on the same matrix, then ultimately you're getting back y actually. Then this will happen only if this is always an identity matrix. Okay, this happens only if this A into A transpose is equal to identity matrix, because some matrix into vector gives the same vector only if the matrix is identity. Okay, so that's why this A into A transpose is equal to I. Clear? That's how you got. Therefore, you will observe one consequence. A into A transpose is same as A transpose into A, of course, and this will be equal to I is one of the case of this matrix. Clear to all of you? Why these matrices are important? Because sometimes you don't want to disturb the magnitude of vectors or things, okay, but you just want to change the coordinate system. So in such cases, all these matrices are useful. Okay, fine. Are you all clear? How many of you learnt orthogonal matrix in a new way for the first time in your life? Yeah, it do commute. A into A transpose and A transpose into A, they commute, because first of all, if you apply A transpose, then what happens? This vector turns clockwise by theta. Then again, when you apply A, it goes back by theta. So it doesn't matter first you are applying transpose and then A or A transpose. They always commute. Correct now? Geometrically you can check that if I rotate this vector by theta and then take it back, or first I take it anti-clockwise and then bring it back, it doesn't matter, the vector x stays there. Okay, that's why it commute. It should commute ultimately. Clear? All these points? Yeah, I know for majority of you it's a first time learning of this kind of thing. Okay, because many people tell you that orthogonal means A transpose into A equal to A into A transpose, but why that comes up is the main thing. Okay, and you have a lot of properties on this. Okay, like now you can see ultimately this implies, since I did not talk the concept of inverse, but I'm just telling one thing. Now if you go to the general case of any general matrix, this matrix when applied on any vector is actually changing the length of this vector. Okay, can anyone tell me one quantity of a matrix will actually tell you what is the maximum length this matrix can stretch a given vector? Let's say for example this is x and this is some k times of x. Okay, so k is some number 2.8, 1.4, maximum it can stretch only to some. The limit of k means any matrix cannot stretch a vector to infinity, it can stretch only up to a particular length. So what decides that? Any idea? Orthogonal vectors product should be null matrix, then why their product is given identity. See, matrix product is where and individual column products is different. Okay, please don't get confused between those two. Clear? Taking the complete matrix product with some other vector is different from the within the individual dot product of the columns. Okay, so please don't get messed up with that. It's actually different. Okay, eigenvalue, no, it's not eigenvalue basically. Of course eigenvalue is indirectly connected, but the main thing is determinant. The physical meaning of determinant tells you that what is the maximum length a matrix can stretch a vector, okay, or shorten a vector. That's what it tells you. Clear? Is this clear to all of you till this points? We have talked some good points about matrix multiplication. Then coming to the orthogonal matrix, we have talked about some good discussion. Then we will see slowly into we have 2-3 more types of matrices, just like nilpotent, idempotent, involutive, this kind of stuff. So once they are done, we'll go for determinants in tomorrow's class. Okay, maybe in the first, because I just want to stop here because it's already 4 minutes less 9. So last 4 or 5 minutes I'll ask you for doubts. If you have any doubts, you can ask me. It's already 9 o'clock. Okay, 3 minutes less 9. How many lectures to take complete the full course, sir? Approximately 48. 6 weeks. Sorry, 8 weeks. I think I need. Doesn't determinant gives area? No. Determinant is actually one of the way to calculate area. That's it. Determinant do not actually give area. Okay. So is there any planning to start class for civil engineering? Yeah, I think the plan is going on. Okay, for English batches. But right now, let's start. We started with maths because this is a common thing to all, and also you need maths for having some good understanding of technical subjects. That's why. And I'm sure you guys might have developed some definitely confidence in me. So I'll be teaching till the last day with the same enthusiasm and also the same concept clarity. Okay, clear? Are you all understanding things? Yes or no? Please type in the chat box, because anyhow last 2-3 minutes is there. I'll just invite questions from you. I'll just quickly go through the things what I have taught you today. So basically we have started with this. Every square matrix can be decomposed into symmetric and skew symmetric parts, which is really very important. Then we have seen some questions based on matrix algebra. Then matrix multiplication is what we have seen, of course, in some detailed sense. So we have seen some important basic ideas of matrix multiplication, properties and all. Then some basic stuff. And product of two matrices cannot be a zero matrix is what we have seen. Symmetric, skew symmetric. Then we have solved some questions. Then came for orthogonal matrix again. And we have seen what is physically an orthogonal matrix is. Okay, so this holds. Okay, guys, I did not put transpose here. Please put it. Okay, previously I did not put transpose, so please put it. A transpose is A inverse. Okay. Yes, zero determinant means basically it can actually keep the matrix at that point. Okay. You're so excellent. Thank you. Thank you, sir. So maths will be over by which month, sir? Because other classes are also going in Parakram batch. It will be taking till maybe 1 month roughly. Okay. 8 weeks means, yeah. Sorry, 1.5 months plus. So how to rotate exactly by 90 degrees orthogonal part? In this matrix, put theta equal to 90. That's what I have done here. Then if you multiply this matrix is obtained by putting theta equal to 90 in the general form. So if you obtain this matrix and if you operate it on any vector, it rotates exactly by 90 clockwise. Okay. Fine. DPP update. Okay, we are planning some practice questions. Maybe it's not like daily practice, but once in a week. Okay, or maybe for one chapter I'll give at a time. Okay, so that you can practice, and if you have any doubts, you can come and ask us back in this Telegram channel. Okay, so these are the links for Telegram channels. You can see we have this is for the English channel. So any update regarding anything on this channel turns up here. So if you feel interested, you can just subscribe. You can just, there's no subscription basically, just you can just scan this, then it directs you to the link. You can click join, and this is managed by me and my students. So this is my group, of course. And as I told you in the last lecture, so please go for this Unity. Okay, so in this Unity we have all these features, and as I told you in the last class, so this unity.pw.live, of course. So if you open, you will see this is a link, unity.pw. If you type, then you'll have this link, and of course once you have this, click on login with Google. So you can sign in with your mail ID, and once you sign in, you will get the page something like this. Okay, so here you can track all your doubts. Okay, so let's say if you ask something, then ultimately you can have a record of that. So what this subname called like matrix and vector clubbed? Submatrices. Okay, we'll see in determinants. Tomorrow when we go for submatrices in determinants, we'll see that. Okay, fine. So then I think 2-minute summary. So basically we have talked about matrix algebra in a broader sense, matrix multiplication, additions, all this stuff we have seen. So anyway, there's more stuff to be looked at tomorrow, and we will look at the concept of determinants, and we'll see physically what a determinant can do when we talk about eigenvalues. Then we'll play with some determinants in tomorrow's class. Okay, some properties here and there. That's it. Okay, so that's the basic idea that we are going to do today in the tomorrow's class. So again, daily at 7 PM I'll be continuing this maths. Okay, so and this course is for free, so definitely if some of your friends are also interested, you can get them here, because this is completely for open resource, so you can learn. Okay, and I hope you are getting the quality education, of course, so definitely you can get it, and these classes will be in English. Okay, that's it maybe. Okay, if you have something to ask, you can ask me, or else it's fine. That's all from my side. Thank you for so much of love here. So many bubbles going on. Okay, so Fine. Are you all having some good understanding of maths? Now I hope none of you are afraid because I am with you. Okay. Thank you all. Fine. So thank you all. Good night. We'll meet tomorrow at 7 PM again, and we'll talk stuff on determinants. Okay. Yeah, thank you all. Take care. And if you have access to this PYQ book, we have launched one PYQ book also. So if possible, get one, because anyhow you need one PYQ book before you get examination. So if possible, get a book, get a copy of that, and please start solving PYQs. Okay, because PYQs really play a very important role. I have done a video and uploaded on the same channel, so you can just look at the importance of PYQs and try solving PYQs. Okay. Yep. Yeah. Thank you all. Good night. Signing off. Bye.